Last week I challenged a geometry problem and it's still not solved. So I'm going to put up a $50 bounty if anyone can solve it, and a smaller $20 bounty for an easier version that I'll get to in a second. As a reminder, we gave a silly definition last time of a wannabe cube. So a normal cube is a rectangular prism where all three dimensions, width, height, and length, are equal. A wannabe cube is a rectangular prism whose width, height, and length are consecutive numbers. So 1 by 2 by 3, 2 by 3 by 4, 3 by 4 by 5, and so on and so forth. And what's cool is that you can cut up a wannabe cube, in this case the fifth wannabe cube, into smaller wannabe cubes of different sizes. That's not true with normal cubes. It is proven that there's no way to cut up a cube into smaller cubes of different sizes. Any way you cut up a cube into cubes, you're going to have a duplicate inside of it somewhere. However, this wannabe cube dissection here is, as far as I know, the only one, so I was interested to find if there's others. So if you can prove that there are no others, or if you find another, I'll pay out $50. And I did manage to show, though, that if another exists, the smallest it could be is a dissection of the 41 by 42 by 43 wannabe cube into the first through the 22nd wannabe cubes. So if you can show that this wannabe cube, the 41st wannabe cube, can't be dissected into wannabe cubes of distinct sizes, then I'll pay out $20. Actually, if you total up how many blocks are in all these wannabe cubes, it's actually a little bit more than the amount of blocks in this wannabe cube, so you have to leave a few out. There's actually a few ways to do that. 5, I think. Yeah, so here's the list of wannabe cubes you leave out to get an exact match. So, 2, 6, 7, 9, what that means is if you were to leave out the 2nd, 6th, 7th, and 9th wannabe cube, the rest of the wannabe cubes here would have exactly the same amount of blocks as are in the 41st wannabe cube. Okay, so why is this the smallest possible solution? It's not the smallest instance of a bunch of smaller wannabe cubes having the same amount of blocks as a bigger one. Besides the example over there, that actually happens here, where the 1st, 2nd, 4th, 6th, and 7th wannabe cubes all together have the same amount of blocks in them as the 9th wannabe cube. The problem is you can't actually fit the two biggest of these inside the target shape. So there's no way to put the 7th wannabe cube in here and the 6th so that they both fit. The widest dimension of the 9th wannabe cube is 11 blocks, and the smallest dimension of this is, 7 blocks. Smallest dimension of that is 6. So together, the smallest width they could take up is 13, obviously bigger than 11. On the other hand here, the largest dimension of the target cube is 43 blocks, or I guess I should say 43 meters, since a block is a unit of volume. And the biggest two cubes you need to fill it are the 21st and 22nd wannabe cubes. So together they would have exactly 43 blocks width if you squish them together. By the way, you could also try the same problem with wannabe squares. So a rectangle whose dimensions are like consecutive numbers, 1 by 2, 2 by 3, 3 by 4. And there are solutions to that, more than just one. So here's one solution, and here's another one. What's interesting is that this solution here and this solution are actually part of an endless family of solutions. So if you were to define a wannabe cube in like an arbitrary number of dimensions, which I think is called an orthotope. It's just called a hyperrectangle. Okay. Yeah, okay, it's called an orthotope. You can actually always dissect the... Let me get this right. So if you're in n dimensions, the n plus 2th wannabe orthotope is always dissectable into the first n plus 1 wannabe orthotopes. So it works in 3 dimensions, it works here in 2 dimensions, In one dimension, this would just mean putting a length 1 line segment next to a length 2 line segment, but it works in 4, 5, 6 dimensions as well. This problem might have also seemed like a bit of a stretch to call a Minecraft puzzle, because I'm kind of just using Minecraft as a platform for a geometry puzzle. But this is one of the few math problems I actually discovered entirely through Minecraft. So Wannabe cubes have a neat property, which is that each of them has exactly 6 times as many blocks in it as a beacon with the same base size. So the 3x4 by 5 Wannabe cube has 6 times as many blocks as the 3x3 base beacon, or, you know, same thing going up to the 7x7 base beacon. And this continues all the way up. Well, -1, you know, because usually you'd have an actual beacon block at the top. I feel like I need to show some cool results since I didn't actually solve this week's puzzle. What made me curious about beacon sizes in the first place was I was trying to find the smallest 2 pyramids who have the same number of blocks in total as another pyramid. And by the way, this is the smallest example. It's the base 9, base 14, added together give you as many blocks as the base 15 by 15 pyramid. You could also look for solutions where the top blocks are beacons and don't count towards the total. One of the other cool things you can do, you can find endless sets of Wannabe cubes or pyramids that have the same number of blocks as another set of Wannabe cubes. I think this is the easiest example to come up with. The Wannabe cubes on the left have the same number of blocks as the Wannabe cubes on the right, and will still have the same number of blocks on both sides if you add 1 to all the dimensions of the red Wannabe cubes. So by smallest dimension, we have 1, 1, 3, 3, 3, 4, 2, 2, 2. If you scaled these up, say, by like 5, so you had the 5th Wannabe cube, the 1st, 8th, 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 9th, 7th, 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 the equality would still hold. Since there's duplicate sizes here, this might not be useful for the dissection problem, but I think you can actually come up with infinite families like this that just have 3 or 4 sizes on either side and are all distinct sizes as well. But that's as far as I'm going in this video, so thanks for watching. I'll see you next time.